the transformation of the strain basically, I think I will try is I will explain to you how the equation be derived, but I won't go to details. And I will let you know what is the starting point, and then I will directly jump into the result. Okay, and we can save time. So, that's fine. Will that be okay?
Good with that.
Good. So we started thinking about from the 2D. So in 2D, if you know the in 2D, then you can generate in 3D just like stress. In 2D, for example, here we have the undeformed element. And here again, I try to explain how we start from. You always distract me. What's up? I don't know what. Okay. This is our default element. So, for example, let me say this has a length as the dimension delta x, and here, for example, here we have let me pick up any point. So, say A, B, C. And say here is our the undeformed shape we pick up for studying the change in the strength, and this side here is delta y. And for example, from here the other side is delta s. And for strain element, usually we have the normal strength, and using epsilon as the notations, and this representing the normal strength in x direction, normal strength in y directions. And normal strength, what I mean, for example, if we have the material like this, if this material is under stretching, so this is the force, okay? Then that is the deformations. For example, if we fix here, okay? So this is the deformation. Deformation is called the delta. Delta divided by original length, and this is the strain. And if we define this is our x coordinates, simply this is the strain, normal strain in x direction. And vice versa, we have the same reasoning in y direction. Okay. And we have the string strain. And usually in engineering we're using gamma xy. The definition is this. If we have undeformed element, this represent is undeformed element. And if we apply the shearing, so for example, the shearing stress could be in this sense, then deformation of this one would become, schematically drawing this one, this wouldn't be so accurate, but that is the meaning like this. So from here you can see this side, after deformation move to here. So here we the material will experience a change in angle. The same on this side. And if the dimensions of this element are, for example, 1, 1, 1, 1 equal in dimensions, then the two angles must be equal. Okay. But in general, the beta representation is this. This will be equivalent to this description. For example, say if we fix one side, we simply put the net of the change in angle into the other side. Okay, so here let me say this is the say alpha, and in general alpha won't be equal to beta in general. But if this is a square, then alpha will be equal to beta. But anyhow, under a given loading or given stress, the summation of alpha beta will be constant. Gamma is defined, if we define this is our xy coordinate systems, then gamma here is simply we subtract gamma xy. Gamma xy is our shear strain. So basically, shear strain is the amount measuring the change in angles. Okay. And for sign convention, this one is defined as positive. So if we have undeformed and then we deform into this, so this is gamma xy is positive. If we have the deformation, so this side, so here is our coordinate system xy. So if the bottom side move to here, so go this direction, and this side go to opposite direction to this one. So under these situations, we simply make the deformed shape. So this one defined as negative. Okay, later we will use a sign, so that is the way to justify. So for this case, yeah, that is positive, and this angle here, this one is defined as a negative. Okay.
And that's all subjected to the same shear for both cases?
The same shear, the amount, yes.
Mm-hmm. Okay.
Yeah. Okay. So with those kind of the definitions for the shearing, then we can study is, for example, if this is an element and the same thing, this element is under shear stresses, then the deformed shape will become like this. Let me only draw the triangles. So A, B, C will be displaced, and then this amount will become the delta x, the original length, plus deformation. Deformation is, what is delta? The delta deformation equal to strain multiply with its original dimensions. So deformations here, this is original length. Due to loading, and this one under certain loading, the deformation, this term will be strain in x direction, multiply with original length, this one. The same thing here, this one will be under strain in the y direction, so original length plus deformation. Deformation is strain in y direction, multiply its original length. In a similar way, this is the whole length here is delta s plus deformation epsilon. That in general is in any angle theta. So here I forgot. So let me say this angle is theta. Theta is an arbitrary index to any orientation we're interested. So this one, epsilon theta represent is the normal strain in this orientation. Okay. Again, epsilon, this one, epsilon theta is the normal strain in these orientations. So this is the strain and multiply with its original length. Okay, so that's it. And then this is theta. And with these triangles, and we always have the relation, the formula for relating the three sides together in terms of the theta. Okay, that is the mathematics we use to derive the equations for transformation of the stress. So under these situations, then we will be able to calculate epsilon theta in terms of the geometry and the strength components.